If you depart here, Dulwich, and opt for a taxi ride to Changi Airport, followed by a flight to Ho Chi Minh City, which is around 1,000 kilometers away. Although your taxi journey is around only 3% of your entire travel distance, the risk of mortality during this short leg surpasses of the later flight. There are many reasons to this, and this will not be true 50 years ago, and even less when aviation first emerged in the early 1900s. So what have this industry done to transform this inherently risky concept to the safest form of transportation on Earth? Frankly, aviation is inherently more dangerous than ground transport. You'll travel significantly faster, while at the same time be faced with thousands more systems, each thousands times more complex. This is the comparison between the part counts of a car and a plane. A car consists of around 30,000 parts, down to the screws and wires, while the 747 have this much. Nope, 6 times as much. So there are many systems in place in aircraft that keep you safe in the air, in the terminal, on the ground, and basically in every part of flight. And one of them is an innovative concept that started its operation since around the late 80s. Traditionally, pilots provide input and aircrafts will fully comply. The yoke or stick in cockpit is connected to a series of cables that will drive actuators, which in turn will lead to a response. Although the plane will comply to all inputs, thus also following all the potentially risky or dangerous inputs too. At high speed, an abrupt pull on the stick or yoke could tear the aircraft's wing off. And here's another one. On Flight 006 over San Francisco, the pilots overstressed the tail control in an attempt of pulling the aircraft out of a dive. In the 1940s, an engineer at Siemens by the name of Karl Otto Altvater modified a Heinkel 111 bomber, removing its cables and replacing it with electrical wires that drive actuators. This technology is also used by the CF-105 built by Avro Canada in 1958, and even utilized in the infamous Concorde. Although, till this time, this technology was only used to save weight and maybe lead to a simpler design of the aircraft. That is until 1987, during the first flight of a new innovative aircraft built by a new company in Europe and boasting its new digital flight control system, a proper fly-by-wire. A modern fly-by-wire is a concept of adding computers into the system. This can protect the aircraft from dangerous inputs such as pitch, yaw, roll, angle of attack, bank angle, speed, etc. For example, one problem pilots face is the risk of an aerodynamic stall. A stall is when the plane goes too slow at too high of a pitch. Without proper correction, the plane will eventually slow down to a point it falls out of the sky, as the wings physically cannot generate enough lift to keep the plane flying. Usually, this is followed by a spin, shown in the video. And it is dangerous in all parts of flight, especially at lower altitudes. However, stalls only happen usually at lower altitudes, thus it is a highly dangerous potential of all pilots that would want to avoid. On the A320, however, it is not possible to enter a stall in the first place. One primary feature of the Airbus fly-by-wire is alpha protection. Alpha is short for AOA, which itself is short for angle of attack. Basically, the difference between where the plane is pointing and the plane is going. The angle between the two is called angle of attack. When angle of attack is too high, the plane stalls. You can look back at the illustration just now. You can see that during the stall, the plane is nearly perpendicular to its flight path, hence suggesting a stall. How to get out of a stall? Well, you just need to keep the angle of attack under a specific value. This can be increasing your speed and also reducing your pitch. So this is what essentially alpha protection do. It senses that the aircraft is about to stall, so it will ignore any more pitch of input and also provide full thrust. Here's a comparison between an aircraft with alpha protection and one without. You can visibly see that the one without getting to a stall and falling out of the sky, while the other keeping its pitch and maybe providing full thrust to maintain its flight. Another notable feature is called bank angle limit. Essentially, when a plane is flying straight and level, all the lift on the wings are supporting the plane upwards. However, once a plane gets into a bank, the lift gets split into two directions, thus less upwards lift. At one point, the plane will no longer have any upwards lift. Usually, this is at around 90 degrees of bank angle. This is also highly dangerous, as the plane can literally fall out of air without the wings supporting its weight. So Airbus have added two types of protections on the A320. One is to restrict the bank to around 67 degrees to maintain flight, and also encourage pilots to around 33 degrees, so it can have a flight that's more efficient, that requires less engine power. In fact, the fly-by-wire is so successful that every single Airbus aircraft after A320 all utilize the same technology. The competitors across the world also used the same technology soon after. This is the 777, which is Boeing's first fly-by-wire aircraft and one of their most successful aircrafts too. They're developing a new version called 777X. Aviation is an industry bold within reason, aimed to reduce risk to the minimum level. So there is inherent risk of the computers malfunctioning, as the A320 and almost every other fly-by-wire aircraft are flew by computers, and the pilots only tell the aircraft what they want to do, instances such as pitch, yaw, roll, and other aspects. So what will happen if, say, one of the computers fail or all the computers fail? Airbus have considered this and have added a comprehensive and very reliable system of redundancies for their fly-by-wire. For example, most importantly, ELAC 1 and 2 are the computers that are controlling the most important parts, the elevator and the aileron. These are the most basic and important flight control surfaces. Without them, the plane cannot have any sort of control. So ELAC 1 and 2 are controlling the important stuff. If either of the two fails, the system moves on to the other. ELAC 1 fails, ELAC 2 takes over. And ELAC 2 is capable of multitasking both aileron and elevator. What if ELAC 2 also failed? Well, Airbus will choose a less important, while still available system that will take over the controls. For example, ELAC 2 fails, SEC 1 and 2 will take over. What if SEC 1 also failed? Say there's a power outage, then SEC 2 will take over. And what if all computers on the aircraft fail? Say there's a catastrophic issue on the plane, there's a fire, or it doesn't have any power or electrical power. Then Airbus have considered this and have added aforementioned cable control as mechanical backup. It will move the trim and rudder of the aircraft in order to keep the plane flying, at least with some control. A lot less efficiently, but it does save lives. This is one of instances when mechanical backup was used. It was in fact the only time pilots had to use mechanical backup to land their aircraft, as computers usually will be able to recover from their issues in midair. In this instance, the pilots managed to land their aircraft with 2 engines lost and all computers lost, simply flying with the trim and the rudder. Thus, this really demonstrated the fly-by-wire's reliability and how the plane can perfectly fly without it. So why am I talking about this? Why am I talking about a flight control system at a TED Talk? Well, it impacts each and every one of us. Human error accounts for 2/3 of all aviation accidents. And unfortunately, human error is something that it's difficult to eliminate. In fact, I don't believe that aviation will ever be able to eliminate all the human error-related accidents in the future. And fly-by-wire is an innovative and alternative design that will be able to reduce the amount of casualties when there are an issue. At one point in the future, it could potentially halve or even fully eliminate the amount of human error-related aviation accidents, thus benefiting us all. This often overlooked piece of technology, it's a seemingly simple yet highly significant factor in the aviation's thrive, contributing to aviation's safety record, thus increasing passengers' confidence. This allowed aviation to thrive safely, connecting our world, and also propelling us forward. Thank you.